Hi all. In this video, we are going to learn about a very interesting and a very simple unsupervised learning algorithm called K-means clustering. So I'm sure you must be familiar with the supervised learning paradigm of machine learning, which is essentially about finding a function that can approximate the relation between the input and the output. So in supervised learning, you are given a set of inputs which are categorized into various classes and the labels are provided. And your job as a machine learning expert is to find out what kind of a mapping exists between the input and the output so that if you are given a new input data point, using your supervised learning algorithm, you can predict which class this new data point belongs to. And that is called supervised learning, and there are many different algorithms within supervised learning like logistic regression, support vector machines, artificial neural networks, and so on. Along with supervised learning, there is another very interesting and equally important paradigm of machine learning, which is called unsupervised learning. So, as the name suggests, in unsupervised learning, there is no provision for supervision, which means that you do not have labeled data set. So you do have some data like you can see on your screen, but that is not labeled, which means that you have the data, but you do not know which point belongs to which category. So if that information was given, then you could do supervised learning, but if that information is not given, then all the supervised learning algorithms actually fail to work. So this K-means clustering is one of the most simplest algorithms in unsupervised machine learning, which helps you in figuring out what are the different clusters that you can form with the given data. And that is the magic, that you may say that if I do not have the cluster or class information, how is it that I can figure it out on my own? And the answer is that yes, you can, and there is a mathematically rigorous way of doing it, which shows that the method actually converges to something that is stable. And that is important because when you run the algorithm multiple times, you do not want to keep converging to very different kinds of clusters. Some variation is okay, but it should not be too different from what the previous prediction was. So before we get into the mathematical description of this K-means clustering algorithm, let us try to understand this using a picture, because as they say, a picture is worth 1,000 words. So here on your screen you see a set of points which are colored green, and we currently do not know what labels each point belongs to. So what we know is that this is a two-dimensional data set, meaning that you have a x-axis which corresponds to some, let's say, input parameter x1, and there is some y-axis which corresponds to some input parameter x2. And now your job is to figure out which cluster each of these points belong to without having any prior information about the clusters. So to begin with, what the K-means clustering algorithm does is that it picks up two cluster mean points at random. So here remember that in K-means clustering, the K stands for the number of clusters which has to be provided as a hyperparameter to the algorithm. So the algorithm cannot by itself figure out the number of clusters, but once you provide the algorithm the number of clusters, then it can figure it out on its own and segregate your given data into the K number of clusters. So here, because visually we can see that there are two clusters, so we choose K equal to 2 over here. So now we initialize these 2 points at random. So one, as you can see on your screen, is marked with a blue cross and the other is marked with a red cross. And now what you do is that all the points which are closer to the blue cross are labeled blue, and all the points which are closer to the red cross are labeled red. So basically this K-means clustering algorithm works on the principle of Euclidean distance, and all the points which are closest to a certain cluster mean, they are said to belong to that particular cluster. So now in this graph that you see, all the blue points are closer to the blue cross and all the red points are closer to the red cross. Now what do? As the name suggests, this is K-means algorithm, meaning that the cluster central point is the mean of all the points in that cluster. What does that mean? So you take all these blue points now and find out their mean, and that is your new cluster point as shown in this graph. And similarly, you take all the red points, find out their mean, and then you get the new cluster point for the current stage or iteration of your algorithm. Now what do? Now you have two new cluster mean points, and then again you do the segregation of the points depending on which of these two crosses they are closer to. So now in this updated graph that you see, all the blue points are closer to the blue cross and all the red points are closer to the red cross, and the separation line between them is shown by this magenta straight line. Now what do? Now we have almost actually converged, but still you may want to run the algorithm a few times to make sure that you are doing all right. So once again you take the mean of all the blue points, and that is your new cluster mean, and similarly you take the mean of all the red points, and that is your new cluster mean, and you keep doing this process till you reach convergence, which, as I mentioned, is guaranteed to happen. Now the convergence may be slow, the convergence may get stuck at a local minima because the cost function landscape may be non-convex. All those problems can happen, but what is the nice thing is that convergence is guaranteed for the K-means clustering algorithm. So this was kind of an intuitive understanding of what the K-means algorithm is doing. Now let us try to formulate it using mathematical expressions. So what we are trying to understand is the K-means clustering. So as I said, this algorithm is a part of unsupervised machine learning. So there are three paradigms of machine learning: supervised machine learning, unsupervised machine learning, and reinforcement learning. So this, what we are going to learn now, is a part of unsupervised machine learning. So essentially, let's say you have n data points which are labeled as xj, where j is going from 1, 2, 3 and so on up to capital N. And you are told that this data points needs to be classified into k clusters. So as I said, the number of clusters has to be given to you a priori. And let those clusters be labeled Ci, where I goes from 1, 2, 3 and so on up to capital K. So you have n data points whose labels you do not know, and you want to find out which cluster each of the data points belong to. So to denote that, to denote which cluster the data point belongs to, we will use this variable rji. So what does this mean? Rji is equal to 1 if the point xj belongs to Ci. So for the points we are using the subscript j, and for the clusters we are using the subscript I. So rji is 1 if xj belongs to Ci, which means, for example, if the point x3 belongs to the cluster C2, then r32 will be 1 and all other rjis are 0. So this is the notation that we will use to figure out which cluster a given point belongs to. So now we have defined our data points, we have defined our clusters, and we have also identified a variable that can denote whether a given data point belongs to a given cluster or not. Now what we need, something like what we did for the supervised learning algorithms, is that we need a loss function which needs to be minimized, right? So in the supervised learning algorithms, be it logistic regression, be it support vector machines, be it artificial neural networks, we always had a cost function which needed to be minimized. Similarly, here also we need the cost function for the k-means clustering algorithm. So as I mentioned earlier in this video, that the k-means clustering algorithm is based on the concept of Euclidean distance, which means that you try to assign a point to a cluster depending on which cluster mean it is closest to. So let us denote the cluster means by the symbol mu I, and then the loss function for k means, it is also called the distortion measure. So the distortion measure or the loss function for k means, let us denote that by capital J, is equal to sum over all I going from 1 to k, sum over all j going from 1 to n, r j I x j, I am using a vector sign to denote the distance, minus mu I whole square. So this xj vector denotes the input data points. The mu i's denote the central locations or the identity points of the k clusters. So our objective of the k-means clustering algorithm is to minimize this loss function. So what are the variables over here? The variables are rji, which denotes which cluster a given point belongs to, and the mu I is the central location or the identity point of the individual clusters. So what is our job? To find out rji and mu I, which minimizes the cost function j. So what does this minimization means? This means that you need to find the cluster means properly and the assignment properly so that the closest points to the mean are assigned to that particular cluster. And if we do that well, then our loss function is going to be minimized. Now let's see how exactly this is done. So we have seen this intuitively, but let's write out in a mathematical format so that it becomes easy for you to implement it using a Python program. So as I mentioned earlier, this is an iterative process, meaning you need to do it repeatedly till you reach convergence, which is actually guaranteed. So this is an iterative process. So what is your step 0? The step 0, obviously, as we also saw in the example, is to choose the cluster mean. So choose the mu I points randomly. So either you can choose it completely randomly or you can choose some data points as well. So here we are choosing the mu I randomly from the given data points. Now what do you do? In step 1, you now assign the rji values for all the input data points. So what you need to do is that for each xj, find the mu I to which it is closest, and then assign rji is equal to 1, and once you have done this for all the xj points, all the remaining rji's will go to 0. Okay, so what does this mean? For each data point, you need to find the distance from all the cluster means, all the mu I values, which are k in number. Out of all these values, pick up the one which is the smallest, and for that particular value of I, assign rji equal to 1, and then you keep doing it for all the j values. And once you have done this, once you have populated your rji values, whatever remains unassigned, that goes to 0. So now this completes your step 1. Now your step 2 is obviously to update your value of mu I, because this mu I and the rji are the two sets of parameters that you need to optimize in order to minimize your loss function or your distortion measure. So you have initially chosen your mu I, using that you have computed rji. Now you need to update your mu I and then using that calculate rji once again and do this process in a loop till you reach convergence. So step 2 is basically that for rji estimated in step 1, update the mu I values. And how do you do that? So now our objective is to minimize the loss function. So basically we need to take a gradient of j with respect to mu I, set that equal to 0. So what will that give us? So here you can see that j is equal to this function. So if you take a derivative of j with respect to mu I, what you will get is 2 times this particular function, and there will be a negative sign also, but that doesn't matter because we are anyways going to equate this function to 0. So now what we have is that this implies 2 times summation j is equal to 1 to capital N rji into xj vector minus mu I vector is equal to 0, and that finally gives you the mu I vector is equal to summation of rji xj over all j divided by summation of rji over all j. So what is summation of rji over all j? This is exactly equal to the number of input points which are assigned the label I. So essentially this is the mean of all the data points which are assigned to the cluster I, and which is what we saw in the graphical explanation. So now what you do is that once you have completed step 2, you again go back to step 1 and repeat the process, but of course before going to step 1 you again remove all the assignments of rji, or you can assign all of them to 0 and then do this process. Then calculate rji, then again update the mu I and keep doing this process till you reach convergence. As I have been saying, that convergence of the k-means clustering algorithm is guaranteed, but it could converge to a local minima. So because the cost function landscape is non-convex, so you do not know exactly whether it will converge to a global minima or not, but convergence is definitely guaranteed. However, if the problem is very complex, then the convergence could be slow, and then there are some variations available which can take care of the slow convergence problem. But this essentially is the essence of the k-means clustering algorithm. A very interesting application of the k-means clustering algorithm is in what is called lossy data compression. Data compression is of course well known to everybody. When you have a large file and you do not have that much space on your hard disk, you want to compress it using zip or rar or any other such softwares. Now those kinds of compressions are lossless, meaning if you compress a file using zip and then after let's say a few months or a few years you decompress the file, you will get exactly the same contents as what were there before compression. And that, as I said, is lossless data compression. But many times you are okay with lossy data compression. When is that required? Suppose you have gone to a picnic and you have a very high-end DSLR camera and you took a very high resolution picture using the camera. Now that is great, the picture looks very good, but because the picture is high resolution, it is a very large sized image. And now when you want to share this with your friends on WhatsApp or Facebook or Signal or any other such app, then you might have trouble because downloading or uploading large files may be problematic. So then you want to reduce the resolution of your image and make it low resolution, which is not that troublesome, which the human eye, let's say, cannot detect that well, or even if it can detect, it doesn't totally destroy the beauty of the image, and that then reduces the file size, which makes it easier to share or store on various social media platforms or even your own hard disk. And this is a example of lossy data compression, because once you have reduced the resolution of your image, it is usually not possible, although nowadays there are some techniques of converting low resolution images to high resolution images, but generally it's a difficult process and it is not completely reversible, and that is what is called lossy data compression. And the K-means clustering algorithm is one of the ways in which lossy data compression can be done. So now let's say you have n data points. So for each of n data points that we had earlier, what you do is that instead of storing the information of the exact location of all these data points, you store only the identity of the cluster to which it belongs. Now this is lossy because once you have stored only the cluster information, you can no longer recover what the original data points were, but if the cluster information is sufficient to do your job, then you don't need to worry about storing the entire information about all the data points. And this obviously uses significantly low data if your k is much smaller than capital N. This is the important criteria, and this method is also called vector quantization, and the mu i's, the cluster means, are called the code book vectors. So these mu i's form a kind of a code book because you are looking at just the code book entries to infer the data points. So now let's take a more specific example and see how this works. So let's take a specific example of lossy data compression. So consider an image. So consider each image in a given data set which has n pixels. So here n is the total number of pixels, not just along one row, and each pixel has RGB values, as it is the case in all kinds of color images, and the values are stored using 8-bit precision. This is also important because the precision that you use also decides how much compression is actually possible. So what this means is that each image needs 24n bits. Where did this 24 come from? So this 24 simply came from 8 multiplied by 3, and that gives you 24, multiplied by capital N gives you 24 capital N number of bits. So for storing each single image with 8-bit precision, you need 24 capital N number of bits. Now our objective is to reduce this or compress this image information into a smaller resolution image where you store information only about the clusters to which each pixel value belongs to. So let's say you have k classes or clusters, and storing information about the k classes or clusters needs log to capital K number of bits. So if you have, let's say, 8 number of classes, then which class a particular pixel belong to will require 3 bits, because 2 power 3 is 8. So if you have a 3-bit storage space, then you can store information about 8 classes. Similarly, if you have 16 classes, then you need 4 bits of information. So if you have k classes in general, log 2k number of bits is sufficient to store the information about which class a given pixel belongs to. And now once you have stored this, you also need to store the information about the classes themselves, which is the code book. So the code book vectors, which is the mu I, which are k in number, because mu I, as you know, goes from 1, 2, 3 and so on up to capital K. So if you have capital K number of vectors, you need 24 k number of bits if you are using the same 8-bit precision to store this. Now if you have capital N number of pixels, then you need to store the class information for each pixel, and that will become capital N times log 2k. So what does this mean? That means that the total number of bits now with the compression is equal to 24k plus capital N log 2k. And now what we need to find is the compression ratio. So what is the compression ratio? That is 24k plus N log 2k divided by 24n, and you can multiply it by 100% to get the answer in percentage. And as it turns out, if your capital K is 10 and your capital N is 10,000, meaning you have an image with 10,000 pixels and you want to compress it using 10 clusters, then there will be a compression of 13%, meaning that your new image will occupy only 13% of the space that your original image required, which is a huge gain. So this is how the K-means clustering algorithm can be used for data compression. Now here finally one important point to understand is that you must have read about the KNN algorithm, and often people confuse between the KNN algorithm and the K-means clustering algorithm. It is very important to understand that these are totally different things and there is no correlation between the two. So you have the K-means clustering and you have the KNN, which is the K nearest neighbor algorithm. So the first and the most important difference is that the K-means is an unsupervised algorithm and the KNN is a supervised algorithm. That is a very, very important difference. And secondly, of course, the meaning of K itself is different. So in K-means, the K refers to the number of clusters. So here in the K-means algorithm, you are given a set of unlabeled data points which you need to classify into K number of clusters. So the number of clusters is given to you in the K-means clustering algorithm, whereas in KNN, this is the number of nearest neighbors which you use for classifying a new data point. So in KNN, what happens is that you are given a already labeled data set where you have some input data points and you also know which label is assigned to each of those data points. And now in using the KNN algorithm, your job is to figure out that for a new data point, which class or which label it should belong to. And to figure that out, you use the value of k there, which is the number of nearest neighbors which you check to assign the particular class to that new data point. So the meaning of k in both the cases is completely different. So this is something that is very important to remember. And please do not confuse between the k-means clustering algorithm and the KNN algorithm. So now this k-means clustering algorithm is a very simple algorithm, yet very powerful. But of course, it also has certain limitations. So as you can see in the graph that you see on your screen, if you have this data set and you apply the k-means clustering algorithm, it will identify the clusters with reasonable accuracy. But as you can see in this region, the points are definitely misclassified and they should actually belong to the other class. But because in k-means you're only concerned about the distance from the mean, that's why your points are misclassified, primarily because this data set is unbalanced. You have a lot of points belonging to one particular class and a few points belonging to another class, and for such unbalanced data sets, k-means clustering algorithm will have problems. Now there is another unsupervised learning algorithm called the Gaussian mixture models, which can address this problem to a very large extent, and that is what we are going to see in the next video. Till then, stay connected.